Olá, muito boa tarde a todos. Sejam bem-vindos à sessão número 3 da 9ª Conferência Passivhaus Portugal. Trata-se de um evento, como sabem, organizado pelo Grid e pela Associação Passivhaus Portugal. Queremos começar por agradecer o apoio dos nossos parceiros de comunicação, o apoio dos nossos parceiros institucionais e o apoio dos nossos parceiros estratégicos. Queremos relembrar os próximos cursos oficiais Passivhaus que vão decorrer em Portugal. Teremos o curso Certified Passivhaus Tradesperson com início em fevereiro de 2022, um curso com vertente mais prática para quem está em obra. E com início também em fevereiro de 2022, a próxima edição do curso Certified Passivhaus Designer, este destinado exclusivamente a projetistas e a quem está diretamente ligado ao projeto e à consultoria. Convidamos também a visitarem o site da associação em passivhaus.pt e a acederem ao menu Soluções para encontrarem as soluções dos parceiros da rede Passivhaus em Portugal, distribuídas pelos diferentes setores. E temos também todas as conferências anteriores disponíveis no nosso site para acederem de forma totalmente livre e gratuita, portanto podem aceder às apresentações em PDF e vídeo das 8 conferências já realizadas. Temos também disponível no nosso site os seminários e workshops que decorreram de norte a sul do país, nas ilhas e também por videoconferência. E vamos então, sem mais demoras, entrar na 9ª Conferência Passivhaus Portugal. Vamos só ver aqui então a breve mensagem de boas-vindas.
Olá a todos, sejam bem-vindos à 9ª Conferência Passivhaus Portugal 2021. Este é o maior evento em Portugal sobre a Passivhaus, por isso pretendemos celebrar e mostrar a vitalidade da Passivhaus em Portugal e no mundo. Os tempos que vivemos têm-se afirmado como tempos muito exigentes, tempos de resistência, em que exigem o melhor de cada um de nós, e são por isso tempos em que é urgente afirmar com cada vez mais veemência a necessidade de construir alternativas aos modelos atuais. São por isso tempos em que é urgente exigir Passivhaus para todos e fazer a transição do parque edificado. O crescente interesse na Passivhaus em Portugal mostra que esta é uma alternativa aceite e desejada. A cada vez maior capacidade instalada da Passivhaus em Portugal mostra que é possível construir esta alternativa. Sejam bem-vindos à 9ª Conferência Passivhaus Portugal 2021. Vamos construir o futuro que queremos.
Vamos só relembrar aqui, mais uma vez, as regras de funcionamento da sessão. Portanto, devemos todos ter o microfone ligado durante as apresentações e devemos ligar o microfone quando quisermos intervir no período de debate e discussão. Mesmo sendo um evento à distância, devemos ter a nossa câmara ligada para facilitar o reconhecimento de quem participa, e a participação oral só será permitida a quem tiver a câmara ligada. Em qualquer momento da apresentação podem colocar as vossas questões e comentários no chat do Zoom, que o moderador irá depois fazer, colocar essas questões aos oradores. Estamos também a transmitir via streaming na página do Facebook da Associação Passivhaus Portugal, e lá também podem participar, colocando os comentários e as perguntas na caixa de comentários que também serão transmitidos aqui aos oradores no Zoom. Este é o programa geral da conferência, portanto, os 2 primeiros dias. Estamos hoje então a entrar na sessão 3, a primeira das 2 sessões internacionais que vão aqui decorrer. Este é o programa da visita da exposição virtual, onde podem já aceder a todo o material que já foi apresentado. E só aqui uma visão rápida sobre o primeiro dia da conferência. O segundo dia da conferência, e podem já rever ou ver, se ainda não tiveram oportunidade, os conteúdos já apresentados nas 2 primeiras sessões. Vamos então, sem mais demoras, entrar aqui na sessão 3. Esta sessão será moderada pelo professor e colega Manuel Duarte Pinheiro, que é professor no IST e é o responsável do sistema de certificação Lidera e também um especialista Passivhaus. Boa tarde, Manuel.
Boa tarde, João. Muito obrigado. Em primeiro lugar, ainda em português, gostava de agradecer e dar os parabéns à organização por mais esta 9ª Conferência Passivhaus 2021 e, sobretudo, para a adaptação que se tem feito em relação a esta evolução, não só nos casos, como também online. Sendo esta sessão internacional, se eventualmente não houvesse inconveniente, se calhar começaríamos agora a apresentar os oradores desde já em inglês e fazer o restante em relação a tudo isso, se achares bem.
Sim. Podemos seguir assim.
Okay. So, first of all, welcome to everybody. Now it's an international session about Passivhaus in Portugal. The first welcome that I want to highlight is Oliver Style, that is already online. I want to present Oliver Style. Oliver Style is an architect and an energy environmental studies consultant. He's a founder of Praxis as Resilient Buildings, that is an organization based in Barcelona, and also, of course, have a very strong expertise in Passivhaus, in which have studied and implementing house concept. So, in this perspective, they are going to present to us a speaker speaks about keep cool and carry on Passivhaus cooling experience in warm climates, in which I highlight some tips and other perspectives. Welcome, Oliver, and good speech, please.
Hi, my name is Oliver Style. I am a Passivhaus certifier based in Barcelona, Spain. CEO of Praxis Resilient Buildings, an engineering company working in Passivhaus low energy buildings in warm climates. So I'd like to share with you a presentation today called Keep Cool and Carry On, Passivhaus cooling experiences in warm climates. So the presentation kind of brings together lessons learned, what to do, what not to do after about 10 to 12 years of working in trying to keep passive houses cool in warm climates, particularly warm, humid climates. And the study is focused mainly on single family homes, but I think with lessons that have been applied to many different kinds of buildings. So where were we 2,000 years ago? Well, at least in terms of average global temperatures, we were here, what you can see at the start of the graph, and then we invented the steam engine, and then things got a little bit out of hand. And as we know, temperatures have been rising since then. So doomsday headlines abound, record-shattering heat waves are being recorded everywhere, warnings that we must prepare for extreme heat, mortality is reported in heat waves in different countries, such as Canada, which traditionally is not a particularly warm climate. This graph too is quite shocking. It shows the peak mortality rate in France during the 2003 heat wave compared with the first wave of COVID in 2020. So what we can see here is that the peak mortality rate was actually higher in the heat wave in France all those years ago compared to the first wave of COVID. Obviously, the absolute numbers are much higher with COVID, but this is really quite telling. What it shows is that heat waves are indeed mortal. So we see temperatures, as we said, temperature records being broken all over the place, worryingly in places such as this, in the Arctic this past June, maximum temperature of 31 degrees, early ice breakup, record temperatures being broken again in June in Mexicali in Mexico, 51.4 degrees, reaching 53.2 degrees in the aptly named Furnace Creek in Death Valley in the US. Coupled with that, we have, at least in Spain and I think in many European countries, a really massive increase in the price of electricity over the recent months, principally due to the increase in the cost of natural gas and its effect on combined cycle gas turbine power stations. So this is another factor really which we have to weigh in, which will be increasingly the case in the coming years. And during heat waves, obviously the stress on national grids and networks becomes more intense as active cooling, air conditioning equipment is turned on. So, of course, the scale of the problem is quite daunting, but if we preach that we are completely screwed, then we probably won't gain many supporters. So we need to focus, of course, on the solutions of which there are many, and particularly in our sector, the construction sector, there are solutions in terms of keeping buildings cool using very little energy, both with passive and active means. And that's what I want to focus on in this presentation. And I hope some of this will be useful for your work and projects. So which climates are we going to need active cooling for in the coming years? Well, we all know that for warm climates, this is the World Climate Map classification according to the Passivhaus Institute. We all know that climates 5, warm climates and hotter, need active cooling. The question is, are we going to need active cooling in warm temperate and even cool temperate climates? I think that will increasingly probably be the case. What we do have to do, of course, is exhaust all passive design strategies before we start considering active systems, air conditioning, refrigeration, active cooling. So this is what I want to run through first before looking at the various different active cooling systems. So passive cooling tip number 1, pay attention to the local climate. When you're modeling your project with PHPP, look at the climate, the official climate data, compare it if you can with data from local weather stations. Make sure that what you're modeling actually has some basis in the local climate conditions, which can obviously change quite significantly once you move in from coastal areas or move up or down in altitude. Passive cooling tip number 2, cool colors. These are traditional Mediterranean techniques, and in many warm climate cultures, painting houses white, particularly roofs, that reflects more solar radiation and stops transmission heat gain, stops the heat getting into the building so much. Passive cooling tip number 3, ground coupling. Here, what we can do is just reduce the amount of thermal insulation we put on the floor slab of buildings. Obviously, this is going to work better on low-rise residential buildings that have a significant amount of their envelope in contact with the ground. But what it means is we can use the ground as a heat sink, taking advantage of the relatively lower temperatures in the summer months and letting a bit of heat dissipate to the ground. Of course, that's also not going to work in very warm climates in which the ground temperature is much higher. So this is also quite climate specific, but it can be a useful strategy. We also need to just be careful of minimum surface temperatures in the winter. If we don't have an underfloor heating system, we need to make sure that if we reduce that amount of insulation on the ground floor slab, we're not going to cause thermal discomfort to users during the winter months. So passive cooling tip number 4, roof insulation. Again, this is all quite logical. It's good to use important levels of thermal insulation on the roof to stop these transmission heat gains coming through in the summer months. Radiant barriers can also be useful to stop radiation heat gains and keep the house building underneath cooler. Passive cooling tip number 5, natural night ventilation and thermal inertia. So again, this is a classic bioclimatic strategy which has been used over centuries. The concept is accumulate heat in the building's mass and then ventilate at night. When you take relatively cool air into the building, that heat is removed from the building structure and then you eject it outside. So we can use the PHPP summer ventilation tool to calculate the effect of different ventilation strategies and openings. We can look at how the thermal inertia of the building also combines with natural night ventilation and how effective that is. Again, these are solutions which are going to work in climates in which the nighttime temperatures are sufficiently low. If they don't drop below 18 degrees or so at night, we're not going to have much cooling power. We're not going to be able to take much heat out of the building with natural night ventilation. So this is also quite climate specific. If we're in a coastal, warm, humid climate, of course, we open the windows at night, we're just going to bring in not only lots of heat, but lots of humidity too. So this is a very effective strategy that needs to be looked at in the right context and climate. So passive cooling tip number 6, ceiling fans. These are useful because they just move air over our bodies. Once there's more air movement, our bodies transpire more. It gives us a sensation of improved thermal comfort. We feel slightly cooler. It's also useful in Mediterranean homes, which are often all open in the summer. We don't shut the windows. So fans can just keep a bit of air movement going, and that can be useful. Passive cooling tip number 7, internal heat gain. So we need to make sure we're using efficient equipment and appliances so that they generate less heat and more of the electricity that they consume goes towards what they're really meant to be doing. We need to pay a special attention to domestic hot water systems, and in particular the recirculation loops in which hot water is circulating around a building, which can be a real killer in the summer. It can be a giant radiator which causes a lot of overheating, or can cause a lot of overheating problems in passive houses. So watch the hot water systems there. Passive cooling tip number 8, the most important one is opening design windows. We need to ideally avoid the temptation to over design windows that are too big. We need to really look at protecting and minimizing opening surface areas to the east and the west, which in the northern hemisphere receive more solar radiation than openings to the south, as we can see in this graph. So eastern and westerly openings, ideally we want to reduce them and make sure they're really well protected. For the winter, minimize northern openings, and to the south, make sure they're also well protected. But east and west are the most critical. We need to ideally have mobile shading devices on all openings, which can be either motorized or at least controlled with some degree of automation so that they're less susceptible to people forgetting to drop them down. We can also use fixed shading devices to east and westerly windows. Those are best vertically orientated, southern openings horizontal, and we can use Design PH, for example, the SketchUp plugin as a kind of shading analysis tool to make sure that our fixed shading systems are effective at actually shading the openings. So what to watch during the design phase? If we're not going to use active cooling, then it's recommended to keep the overheating frequency, that percentage value that the PHPP verification page will show you, keep it below 5%. Okay, we know that we can get up to 10% in certified passive house building, but really we should be below 5%, ideally below 2%. It's also good to question your assumptions about user behavior. So ask yourself, are people really going to open the windows at night? Are they going to leave them fully open? Are blinds going to be up? Are they going to be down? Is there going to be noise in the street? Is there going to be insects? You know, what's going to happen in reality, and how realistic are our assumptions? It's also recommendable to check zone by zone overheating in large and especially tall buildings in warm climates, if needed with dynamic simulation tools. And important to look at the urban heat island effect in future climate scenarios, which we can do in the PHPP with a climate tool, which takes into account those two effects. So we can stress test our design and make sure it's robust in the absence of any active cooling. So passive cooling, when will it not work? Well, there will be many situations in which the passive cooling strategies won't work. The ones I've just presented here. One example is what you can see here of a week in Barcelona during the heat wave of 2015. So what we can see is that minimum night temperatures in many of the evenings didn't drop below 24 degrees. So if you ventilate in the night, you're not going to take any heat out of the building. In fact, you're just going to heat it up more, combined with large amounts of humidity and outdoor air, which you can see in the graph on the right. So passive cooling in these kind of situations isn't going to work. And here's an even more extreme example of temperatures this last July in Furnace Creek in Death Valley in the US. Minimum temperatures of 41 degrees, maximum 54. So obviously here, if you open the windows at night, you're not going to cool anything at all. It's absolutely impossible to maintain comfort with passive cooling strategies in these kind of climates. Passive cooling does work. There are multiple examples of it. Here's a small single family home we monitored again during the 2015 heat wave, and you can see temperature and relative humidity on the comfort graph with really temperatures in the optimum comfort range, just moving outside of that, basically when the occupants weren't there, the red crosses, when they weren't there to ventilate the home at night. So passive cooling can work. This is a climate in Barcelona, but about 900 meters above sea level in the province of Barcelona, but a little bit higher up in the mountains. So temperatures drop in the evening and passive cooling can work. So once we've exhausted all of our passive cooling strategies and we've worked out that we really need some active systems to maintain comfort, what are the alternatives? Of course, there are multiple different systems. What I wanted to present here are 6 different ones which we designed, installed, implemented, and monitored. And I've put them together in this table, which just with a quick and simple point scoring system looks at design, installation, and commissioning simplicity or complexity and cost. One being the most simple or the most economical, and then looking at efficiency, comfort, and peak load capacity. So peak load capacity is how capable are these kind of systems at dealing with extreme temperatures during heat waves. So the first 2 systems are radiant cooling systems. One is underfloor with dehumidification, and then the other is, number 2 is radiant ceiling with dehumidification. Okay, I'm going to run through each one by one, but just to summarize them. Number 3, low temperature radiators, basically floor mounted fan coils, which is both convective and radiant cooling. And number 4 is a classic passive house solution of incorporating a cooling coil on the supply air stream and just cooling using the ventilation supply air. 5 and 6 are conventional air cooling systems, 5 being fan coils, i.e. water distribution, and 6 being splits or refrigerant distribution. In both cases, those can be either wall-mounted or ducted fan coil or split systems. So the technologies we're looking at here are all based on basically heat pumps involving a vapor compression circuit, which is what you can see here in the image. So number 6, a direct expansion system, basically takes heat from a room, passes it to a refrigerant through the evaporator. That goes through a compressor, which changes its phase. That means the refrigerant is able to absorb and release large amounts of heat. That heat is then taken outside to outdoor air via the condenser, and the cycle is repeated. So this is the direct expansion heat pump system. And then systems 1 to 5 include a secondary water circuit. So here we're taking heat from the room with an evaporator, passing it to water with a circulating pump that then goes through a heat exchanger. The heat is taken from water to refrigerant, and then again through the direct expansion refrigerant cycle, we're taking heat outside. So this is basically the technology, heat pump cooling technology, that we're talking about in these systems that I'm going to present now. I'm going to present monitor data which shows air temperature versus relative humidity. We're looking for data within the optimum comfort range, which you can see here, and then the PHPP calculations. When we're working with PHPP, the tool is basically trying to keep us within the range you can see here. We're looking at air temperature, not operative temperatures, which are obviously difficult and expensive to measure. And most importantly, in humid climates, we want to try and keep indoor absolute air humidity below 12 grams per kilo. Okay, so once we select active cooling in our PHPP tool, you'll see that there's that frequency of excessive humidity which can't exceed 10%. So that means that we can't have over 10% of hours in which the internal absolute humidity is greater than 12 grams per kilo. That means that 25 degrees operative temperature and 60% relative humidity is about the upper limit for comfort. Okay. This is what we can see in the high humidity index on the PHPP tool of 12 grams per kilo. So system number 1, this is a radiant underfloor cooling system where we used an underfloor system with a dehumidifier in the ventilation supply airstream. What we did here was incorporate a recirculation loop. Recirculating indoor air, which is not a good thing to do in times of COVID, but this is what we decided to do to increase the power, the latent and sensible cooling power, by taking air from a corridor, right, incorporating another fan, an on-return valve, and then recirculating a large part of the air and allowing fresh indoor air to come in just for indoor air quality requirements. Okay, so the dehumidifier was in the ventilation supply stream with a recirculation loop here. So that took moisture out of the air and cooled the ventilation air, and then we used an underfloor system to run water at about 17 degrees through the pipes. We can't run an underfloor cooling system in which the floor surface temperature drops below 90 degrees, basically for comfort reasons. If people are barefoot or wearing sandals, you can't drop the temperature of the floor too low. So what that means is you can't get too much heat out of the floor, about 30 watts per square meter. On the other hand, you have a lot of surface area to work with, so you can compensate the lower cooling power per meter squared by having a lot of square meterage. Obviously, it's best on tiled or ceramic floors, better to avoid parquet timber floors. We recommend, if you do use underfloor cooling, is to use low inertia systems, which have a quicker response and have less mortar, less mass above the pipe, so that they're quicker to respond. And also recommendable to use plastic manifolds to avoid condensation problems. So monitor data here from a terraced single-family home you can see during a month in July 2019. So a few hours in which the air temperature moves into the extended comfort range, but pretty good. Humidity below 60%, and in general good conditions. So the response from our clients in this case was basically positive. What we have found was this kind of system is very susceptible to control system issues. There need to be temperature and humidity sensors in all rooms to control condensation. There can be more maintenance problems. These are more complex systems to commission and to maintain. They're also more susceptible to people opening windows and humidity coming in warm climates. So, my conclusion is that they're not necessarily the most robust, and they're not always the best at dealing with peak heat wave conditions. So this system number 2 is a radiant ceiling. So instead of using the floor, we're using the ceiling. We're using plasterboard with 8mm water pipes running through them and insulation on top. These are located in the ceiling. We can run water temperature slightly lower than on the floor because of the comfort reasons. We don't walk on the ceiling, obviously. So we can get a little bit more heat out of a ceiling than we can out of a floor. We need to think about lighting and fixtures in a design phase, and obviously users in the future, if they want to hang some new lights, they need to be careful not to draw through the pipes. Important to locate manifolds at ceiling height for commissioning to get water out of the circuits, which can otherwise be complicated. And what we did on this system was, again, as with the underfloor cooling, we incorporated a dehumidifier in the ventilation supply airstream with a recirculation loop. Here you can see some images of the recirculation loop, dehumidifier, the fan, the silencers, and on the right, images of the ventilation ducts. The ones with silver insulation are the supply air ducts. And then to the right, you can see the ceiling, active ceiling cooling panels, which are the ones taking where cool water is circulated. Here's data from only a very short period of 9 days for the single family home. This is a master bedroom, so not a very long time period to look at, but at least the conditions during that period were good, or within the optimum comfort range. Again, as with the underfloor system, we found that these are systems that can be complex to maintain, basically due to complexities in the control system. They're also more susceptible, of course, to windows being open, humidity coming in, and not always that good at maintaining comfort during heatwave conditions, and also systems that have a higher cost. These are not the cheapest. System number 3. So these are floor-mounted low-temperature radiators or fan coils. So we implemented this in a single-family home in the province of Barcelona, but about 900 meters above sea level, so a warm but not especially humid climate. We can run water temperature supply at about 7 degrees on these kind of radiators. So the maximum cooling power depends on the model and length of the radiator. But to give you an example, about a radiator about 1.8 meters long will give you about 2 kilowatts of cooling power. So in this home, we located 7 different low temperature radiators, 3 on the ground floor, 4 on the first floor. Here you can see some images of the low temp radiators on the ground floor. And here you can see the monitored results of for 1 month during the summer of July 2019. So basically good dehumidification, that's kept down below 60%. Some hours in which temperatures are into the extended comfort range, but basically pretty good conditions, very positive feedback from the client, and a good solution. Again, if this was a house on the coast, we wouldn't have such good data. These are low temperature radiators which have less cooling power than what a fan coil or split system would have. So perhaps not so recommendable for very humid climates, but at least here it's worked well. System number 4, this is the classic passive house concept of using the ventilation system to heat or cool the building. So here a cooling coil is located in the supply airstream, and what we did also to provide more power, as we did with the radiant floor and ceiling systems, we incorporated a recirculation loop to increase power. Now what we found is that at least in single family homes where the heating cooling loads are fairly high or can be quite high, peak cooling loads can be quite high. The problem is basically to do with power. We can't supply water temperature too low for these kind of systems, otherwise we found that there's condensation on the casing of the cooling coil. And the cooling power is limited by basically the temperature difference and flow rate. For example, if we are in a single family home with about 180 square meters of useful floor area, and we're supplying air at 15 degrees and ambient temperature is 25 degrees, this is the cooling power that we can get. So it's 500 by the specific heat capacity of air multiplied by the temperature difference. So that's about 1.7 kilowatts. For a house of 180 square meters, that's only about 9.1 watts per square meter. So that's not really enough power, even for a passive house. This might well work. This kind of system might well work well in multi-residential buildings, which are small, compact, and where cooling loads are lower. But what we found is that at least in single-family homes, we get results like this. So a lot of hours in which we move into the extended comfort range. Really not good at all at dealing with heat wave conditions. And in our opinion, it's best just to keep ventilation for ventilation and separate the cooling system from the ventilation. A cooling coil can be useful in the spring and autumn months just to keep temperatures comfortable, but really once you get into June, July, August in warm climates, it's just not enough power from a system like this. So system number 5, we didn't have any monitored data for, so I'm just going to present system number 6 here, which is a similar technology, but here we're dealing with all refrigerant distribution, so we're just doing air to air. Heat is moved from the inside to a refrigerant and then taken outside with ducted split units, as you can see here. So with refrigerant direct expansion systems, we can get really good dehumidification because the refrigerant can be at a lower temperature than the water can also be sometimes too low, but we can generally get good or better dehumidification with split systems than we can with fan coil and water distribution. Maximum cooling power depends on the model and size of the split unit, but for example, with a 20 centimeter high, 75 centimeter wide ducted split unit, we can get 6 kilowatts of cooling power, and that can modulate down to 1. So in a passive house, that's interesting because it means you can run these kind of units at low flow rates. That means that it's more comfortable, better, more efficient, less energy consumption, and less noise. But then you have that cooling power if you need it under heat wave conditions. You can crank it up and still maintain comfort. So here we're looking at an example of a single family home with a ducted split unit on the ground floor. As you can see here, this was a 3.5 kilowatt system. And here we can see monitored data. So the monitored data doesn't tell all the story here, mainly because the users were out of the house when the temperatures are higher, and then they come on and turn it on. Here you can see when they've come in and turned the system on and off, not perhaps an optimal, not at all an optimum control strategy. It would be best to run the split unit at a fixed temperature setting and low flow. But the clients are happy, so they're very comfortable, energy use is low, and under heat wave conditions, they've had absolutely no problems. So of course, what we need to watch with active cooling systems is the global warming potential of different refrigerants. Here you can see a graph of a comparison of different refrigerants. Note the logarithmic scale on the vertical axis. So we really need to start thinking about the environmental impact of refrigerants, looking for low global warming potential refrigerants, and there are increasingly more manufacturers offering propane systems, that's R290, or methyl propane, R600A, and H3 is ammonia, used already on a large scale in industrial refrigeration, supermarkets and so on, and then CO2, which of course has a global warming potential of 1. So gradually all these other refrigerants will be phased out as the global warming potential becomes more of an issue. Something to bear in mind as well, countries which don't have legislation that's perhaps very demanding warm, hot climates, where a lot of air conditioning units are going to be installed in the next few years, this could be a real problem. So important to take into account the global warming potential of refrigerants. So conclusions, keep it simple. That's one of the main things we've learned. Also important to exhaust all passive cooling strategies before we look at active cooling systems and air conditioning. That's the beauty of passive houses, is to optimize your thermal envelope, and then your HVAC systems are simpler and cheaper to design and install and use. So warm and humid climates, important to use equipment that's really been made and road tested for cooling and dehumidification. Okay, that when there's a lot of moisture in the air and you're running cool fluids around the place, condensation will happen wherever it can, and so it's important to use equipment that's really up to the job. I think also good to make sure occupants are aware of the operation and limitations of their system. So when there's a building handover, whether it's a large building or a single family home, important that the occupants or the managers of the building are aware of what the limitations of their system is. Our conclusion is that it's best to leave ventilation for ventilation, separate it from cooling, dehumidification and heating. And we found that convective air recirculation systems, fan coils or split systems are the most robust and the ones able to provide sufficient power during heat waves. And in passive houses that have low cooling loads compared to conventional houses, that means that they can run at lower flow rates, they're quieter, they're more comfortable, they're more efficient. But you have enough power to deal with peak cooling load situations. Split systems with refrigerant distribution offer greater dehumidification power, which can be useful in humid climates. They offer a faster response. You're going air, refrigerant, air, instead of air, water, refrigerant, refrigerant, air. And they will also have lower auxiliary electrical power consumption from pumps. The compressor is moving the refrigerant around, not a pump moving water, and so on. But important again to watch the global warming potential of refrigerants. And with direct expansion variable refrigerant flow systems in larger buildings, it's interesting to think about heat recovery with 3-pipe systems, in which instead of taking heat and dumping it to the outside air in the street, we can condense to water and preheat domestic hot water and save energy rather than heating air in the street. So thank you to all of these people who provided information and data for this study, and above all to you for your attention. It's a pleasure to be here, and I hope you have a great conference. Thank you very much.
Thank you very much, Oliver Style. It was a pleasure. I think we have lots of, you give us an important insights about tips, about strategies. I think it's a lot of questions in mind of everyone, but if it's possible to you, I will wait for another presentation because you can have cross analysis of both strategies, even that is different, if you allow. Is possible for you?
Absolutely fine. Yes, of course.
Wonderful. Okay. So now, thank you very much, Oliver. Perhaps we can have a clam your palms by the presentation. Okay. So now, together with Oliver, in this session, we have also another important and perspective from Juraj. Juraj is also known as Juraj Mikurcik, and is a project architect in which, for example, have been engaged in St. Luke's Primary School. It's one of the schools that have been awarded by BREEAM Excellent. After he works in a neighborhood design Blackwell Community Living Center. Besides extracurricular like biker, he likes to have looking for approach in the timber, in which they develop a methodology called Brett's Straw, and have using innovative approach for Welsh timber. Also design several private houses and primary houses with prefabricate approach, and I think is highlights very much what is the bio-based materials, and is of course a passive house in which they look for prefabricate timber and straw panels, clay plaster, and local cedar cladding. Today, I think George will highlight all way project in which they look for the three important aspects: design, construction, and also the results as monitoring. Thank you very much. Please, the floor or the web is yours in this case. Thank you very much.
So, hola, and thank you for the invite to speak at the conference. I'm very happy to share our experience of designing and building Old Holloway, which is our own passive house in Herefordshire in UK. It's a project that was completed about 4 years ago. We have lived in it since then. Here are some basic statistics. I'm not going to go through all of them in detail, but it's a relatively small house, just under 100 square meters. Unfortunately, form factor is not very favorable. It's about 4.6. But it's due to certain site constraints. I work as an architect, as a passive house designer as well. So I was kind of responsible for design and then for the passive house side of things. The main builder was Mike Whitfield, and also had some help from Alan Clark, Nick Grant, and many other specialists. Here are the passive house certificates, and the project also won UK Passive House Trust Award in 2018. For small projects. So very briefly, it's a south-facing site. It's on top of a hill. If you imagine rolling hills in Herefordshire, we are overlooking the south side of Herefordshire with far-reaching views. We are kind of surrounded by a cluster of existing houses, but there's very little shading coming from either east or south. There's a little bit of shading on the west with some high hedging, but generally speaking, it's a very sort of open site. So there were some existing small buildings on the site before we built the house. There was sort of agricultural sort of nature, small huts, and we decided to locate the new house at the northern part of the site, really to sort of maximize the potential of the site and maximize the views. The site we also sort of cut into the ground to lower its impact to neighbors and just kind of sit within the landscape really discreetly. Here you can see on the left the original site, so the two small huts at the bottom left, and on the right hand side the kind of proposed design with the house added to the northern part of the site. It's kind of not far off how it actually ended up. So just a little bit about the design process, the massing study. So we sort of started off from a conventional 2-story high house-like building with a fairly conventional pitched roof. And then in order to kind of minimize the visual impact on neighbors, we dropped the massing to a 1-story, which meant that we had to increase the footprint of the house. We then also lowered the roof pitch further to about 30 degrees. That sort of ties in with roof pitches of the kind of neighboring properties and minimizes the impact further. And then lastly, we created this veranda to the south elevation, which provides a good shading and just provides this kind of added living space, which is external. And on the right-hand side, there's a very sort of basic schematic of how the house is designed or laid out. So in the central part is very sort of open plan accommodation. So that is your kitchen, living room, and dining. At the top is actually the kind of western wing with 2 bedrooms and the main bathroom. And at the opposite end, behind the living room, there's an office or something that can double up as a spare bedroom with its own ensuite shower room. Here is a sort of larger version of the floor plan. So it just kind of shows the flexibility of the layout. The house can function as a 2-bedroom or a 3-bedroom house, kind of depending on the needs of the occupants. I mean, I was very happy to spend the previous 18 months during lockdown in the office and kind of worked from home. That worked really well. I'm now sort of back in the main archetype office, which is quite nice. But yeah, it just worked really well during that pandemic. The section of the house is very simple, and we kind of used a little trick to increase the sense of spaciousness, and we sort of opened the ceilings up. So the internal space basically follows the pitch of the roof, giving it sort of bigger volume. And yeah, from outside the house seems relatively small, but internally it really sort of feels generous and spacious. On the section on the right, you can also see the kind of covered space outside of the south elevation, that kind of veranda, which is fully shaded in summer. In terms of elevations, we kept them deliberately very simple and kind of use references to local vernacular, simple agricultural sheds. So the window design is also very simple. The windows are designed to optimize views and daylighting. Yeah, they sort of resemble simple agricultural buildings in the area. In terms of sort of materials, building materials and finishes, we kept them, again, very simple. So we used charred timber cladding, which is locally sourced, and corrugated roof, metal roof. Now, in terms of sort of summer comfort, again, the design was relatively simple. We sort of tried to design out overheating by this kind of south veranda that mainly provides the shading for the glazing facing south. But that was also complemented by some external blinds, roller blinds, which we have on, I think, 3 or 4 windows. And again, they provide good shading against the summer sun. MVHI unit also has an automatic summer bypass, so that helps us to keep the overheating to the minimum. And also the exposed concrete slab sort of acts as a bit of a sort of heat battery. So it helps to kind of smooth out the temperature peaks and troughs during the kind of heat waves. In terms of ventilation, we have a very simple ventilation system based on Zehnder Comfo Air MVHI unit. The medium rate is about 100 cubic meters per hour. and that's worked really well. Yeah, glazing is the usual kind of triple glazed system. And in terms of services design, the main space heating strategy is a wood burner. So we have a 4 kilowatt wood stove supplemented by 2 bathroom tower rails. So one in each bathroom, which is kind of running off the hot water cylinder. The hot water cylinder has a sort of integral air source heat pump. So that's a unit that is sitting inside a small plant room. Next slide is a very simple schematic of the ventilation system. So we kept it really, really sort of optimized and simple. So we are supplying into bedrooms and into the main living space, and then extracting through bathrooms and the store. But yeah, kept it as a very kind of compact system. Now we'll get into construction. So what we try to do with the construction is to kind of use materials that have low embodied carbon and footprint. So this was the first example of using prefabricated straw panels by Ecocon in UK. It's a high performance kind of panelized system that uses timber and straw, and it's also a certified passive house component. So we were really excited to use this as the kind of first customers in UK, and yeah, the process worked really well. All the panels are really sort of accurate. They're sort of made to measure, and they kind of work in millimeters. So the panels come together really easily, like a giant kind of Lego blocks. We had sort of really simple strategy for air tightness. Basically, the walls are wrapped in air tightness membrane from the outside, and then additional wood fiber insulation is installed before the final facade is installed as well. We'll get on to details in a little while. So this image is an example of the panel project. So basically, once the architectural design was done, the drawings were modeled and panelized by Ecocon, and yeah, this kind of just showed all the different panels that went together. And it's a very simple and intuitive way of visualizing how the construction comes together. Here we have a couple of examples of typical details. So on the left-hand side, we have a junction of external wall and a roof at the verge. So it's quite interesting to see on the external wall, obviously the air tightness membrane was running on the outside, but then for the roof, it switched to the underside of the roof. So it was important to maintain that continuity of air tightness layer. For the actual roof, we used timber I-beams, and for insulation, we insulated the roofs with recycled cellulose called warm cell. So all the gaps in the roof were fully filled. Now it's probably important to mention the air tightness membrane for the walls is actually very vapor open with a really low SD value. So there's minimal kind of risk of condensation in those walls. Now the detail at the right-hand side just shows the foundation detail. So the straw panels are sitting on the edge of insulated concrete foundation. Again, kind of showing no significant thermal bridging there. And here we have a typical sort of window installation detail. Again, sort of showing how we have sort of minimized the thermal bridging in that installation. We sort of positioned the windows approximately in the middle of the wall assembly. That is the optimal location for a window in terms of heat loss point of view. And at the head and the window jambs, we have sort of wrapped the window frames with the wood fiber insulation, so that sort of minimized the heat loss even further. Okay, now we're getting on to some site photographs. So starting with the insulation under the foundations. So we had 250 millimeters of EPS insulation. And this system was ISOQUIC. It included integral upstands at the edges. So that provided its own kind of insulated shuttering before the concrete was poured. Here we see the concrete pour with some reinforcement in the slab. This was a very hot day, so guys were really working hard to make the concrete sort of nice and smooth. Then the concrete slab provided us with a good base for building the straw panels. And the external walls went up really quickly. I think all the walls went up in 3 days, and the roof took another sort of week or so. So for us, it was really, really great to have the building sort of weather tight within a short period of time. Here we see the roof members. So it was a combination of 400 millimeter I-beams generally, and 200 millimeter I-beams with 200 mil of solid timber beams that were sort of cantilevered out to form the veranda. And again, that detail was achieved the kind of almost zero thermal bridging, but it was all part of the kind of really detailed planning during the design stage. Here we see how the panels looked from inside during the build. So it's actually one of the great advantages of the system was that it's a very dry system. There were at that point very few kind of wet trades, so it was really nice to kind of work in that environment during the construction. On this photo, you see the plywood boards around the window openings, and those were also part of the air tightness strategy. So all the corners in the plywood were taped before the windows were installed. And this shows a junction between walls and the roof, where the membrane from outside is switched to the inside, and then is taped onto a glulam wall plate, and then later on there was a membrane applied to the underside of the I-beams. Excuse me. And yeah, so we make sure that the air tightness layer is continuous. This is just some pre-taping of windows before the installation, and insulating the roofs with recycled paper. That was quite fun. I think we had many tons of shredded newspaper in the roof, which is keeping us nice and cozy. Obviously, as on every Passivhaus project, we had to do a couple of air tightness tests, and we passed quite comfortably. This is the first air test that we've done once we had all the windows in and all the air tightness was kind of taped up and achieved. So the first test achieved about 0.4 air changes per hour. And you can see in the picture a very small fan that was installed within the window, rather than usually a larger fan is used in the door. You'll also notice a small wood stove here in the corner. That was one of the kind of weak points in terms of air tightness, because yeah, inherently it is a penetration through the air tightness envelope. But even the large sort of sliding door was relatively airtight, so there were no major sort of air leaks through that, as you know, we have shown here with a smoke test. Then we sort of carried on with installation of internal sort of partitions. We added really dense plasterboards called Firmacell. So this also kind of helped us achieve more thermal mass in the house. Obviously, straw being quite lightweight, we tried to put a bit more density in the construction. And this is installation of acoustic timber ceiling with my dad. That was really fun. And then we embarked upon a long process of clay plastering of all the kind of straw panels. So Roman from Slovakia, he was an excellent plasterer. So we spent about 7 weeks applying several layers of clay plaster onto the straw walls. And this really provided a great finish that sort of is low toxicity, very natural, and it doesn't need kind of painting. And it's a great combination with straw in terms of kind of achieving good air quality inside and this kind of feeling of solidity as well. Just some details of preparation before the clay plastering around windows. So we applied some reed mats onto the plywood panels to improve the kind of key for the clay plaster. And this is a kind of finished corner. So Roman came up with this kind of idea of a curved reveal, which is really kind of gives it a nice sculptural kind of form. And the finished product there. Then we obviously had to commission the ventilation. So Nick Grant and Alan Clark came around to commission the ventilation system, which was great. And yeah, it's been running really well since then. We also had fun charring the cedar cladding on site, although it took quite a long time to do. I think the final sort of effect was worth it. Here we see a large scale detail of a typical window installation from the outside, and this includes an external blind, roller blind, so that we use that during the summer months or even sort of spring and autumn when it's really sunny. And the great advantage is that it also acts as a bit of an insect screen, so we can leave the window open behind it, and yeah, it's just a really good product and good concept. And a few photos from inside. So yeah, the kind of open ceiling of the main living space with clay walls. So this is showing the kitchen, dining, and living room. This is a shot from the other side. Mitch, our spaniel, is enjoying the comfort of this house as well as we do. And just a photo of the exterior of the veranda. So sometimes in summer we sort of extend the covered space by this kind of sail, external sail, and that just provides extra bit of shading for that timber decking. It doesn't provide any more shading to the interior, but it's just nice to be kind of sitting outside with friends. Now this is a shot of the winter. The first winter after we moved in, we had this spell of really cold weather called Beast from the East in 2018, and it was a first huge test of how the house is going to perform, and it was absolutely fine. Just a few more interior shots. Now, I'd just like to cover a few things on the performance. So since the completion, we have been monitoring the temperature, CO2, and acoustic levels inside, and humidity. So the graphs on the one on the left shows the kind of summertime. The graph at the bottom is the interior temperatures. So it's kind of hovering around 20 degrees C, even during the kind of heat waves. So the blue line is the inside temperature. The red line is the external temperature. So even with temperatures sort of nearing 30 degrees, the inside kind of stayed well below 25 degrees C. And then the graphs on the right-hand side is the kind of winter time during the beast on the east. So again, the red line is the external temperatures. So for a period of about a week or 10 days, it went sort of well below zero, which is quite unusual for UK. But again, the inside temperatures barely touched or changed during that period. So they were, fluctuating just above 20. Now, in terms of the heating demand, the PHPP predicted just under 15, but the actual heating demand, kind of based on the wood that we burned over that sort of really cold winter, came to about 9.5 or around about 10 kilowatt hours per square meter. Just for comparison, last winter we burned 1/3 of a cubic meter of wood, so it would be even lower than that. And I'll come on to the question of wood burner in a short while. And again, yeah, this kind of shows a larger version of that summer heat wave. Again, showing the external temperature in red and internal temperature in blue. So yeah, kind of very stable conditions. Now, it was also very fun to join the Passivhaus Challenge earlier this year. Mark Siddle from UK on Twitter started this kind of fun little activity asking residents of passive houses to basically stop the heating for a week and see what happens. So a few people on Twitter kind of joined this campaign, and it was just quite fun to see how the house would actually perform over that time. And in the end, it was really easy to kind of stay there without heating for a week. So it started on 19th of February. We turned the heating off. Outdoor temperature was it was relatively mild, sort of anywhere between sort of 4 and 10 degrees outside. But yeah, inside temperature sort of hovered between sort of 19 and 21. So again, it just showed that passive house is very kind of resilient in terms of how it behaves in terms of power cuts, or if there suddenly there was no power available, would probably be still okay for a while. And the next one is just to show our consumption of air source heat pump. So these are kind of weekly readings, and they sort of fluctuate during seasons. So the kind of summer performance is a lot better. Kind of weekly consumption is about 10 kilowatt hours per week, whereas in winter time it does go up to about sort of 70 kilowatt hours. Now, our original SOC pump did malfunction last winter, so it had to be replaced. As you can see, for a short while we just used immersion heater, and the consumption went really high. But now the consumption is back to sort of where it should be. So at the moment, yeah, it's around about sort of 10 or 12 kilowatt hours a week, which is really good. And here are just a few thermal images, just kind of trying to find any cold spots. But as you can see, the hottest and coldest things are things like the television and the cold bottle of beer in the house. So yeah, very happy with how the system and the building has been sort of constructed with almost no kind of significant thermal bridges. Now, Joao, you asked me to include things that we would probably do differently. So now we've lived in the house for 4 years. I think it's become clear that the wood burner is probably not ideal for us. I mean, one thing, it's quite expensive. It was quite expensive to put in. We don't actually use it all that much. So if we did it again, we probably wouldn't install it, and instead we would put a mini split that would kind of supply the small bit of heating that we need, but also could supply a little bit of cooling in summer just to kind of improve the comfort. We could also use the space better that's currently occupied by the wood burner. So yeah, I think the wood burners are really a thing of the past that we should just kind of forget about in passive houses and any other houses, to be honest. And the other thing we would probably look at is the foundations, because we are conscious that materials have a carbon footprint. So with the straw panels and timber roof, etc., we were sort of had quite good credentials, whereas the foundation was still quite high in carbon. So we would probably be exploring alternatives for foundations that could include either suspended timber flooring or something like foam glass and limecrete or clay floors. So yeah, that would be definitely something we'd look at if we were building the house again. And obrigada. I think that's me done. Thank you very much.
Thank you very much, Juraj, or George, as you wish. Thank you very much. So I think we have two excellent presentations in which I like different topics. I open to the questions, and I ask João Gavião for help me if there is anyone. I have lots of questions also, but I will wait for the participants in the conference. First questions for Oliver. If there is no one, I can break the ice. So, begin by Oliver. So, I have one, if nobody have anyone. Okay, you mentioned several passive cooling strategies. And I have two questions. One is more easy, another will be more tough. So, what do you think that are more effective for a warm and humid climates? In some cases, Barcelona and Catalonia is very similar for some of the areas of Portugal, not in the north, of course, with some adjustment. So what do you think is more effective? The second one is, what will be more cost effective?
Okay, is the question in terms of passive solutions?
Yes, about your strategies, cooling strategies that you have highlighted and you put some tips, something like that.
Okay. Yes, I mean, I think what we've found is that warm, humid climates are the most complicated ones for designing any kind of building, but especially a passive house building, because you have lots of humidity. You don't have very high temperatures, but you have high minimum temperatures in the nighttime in the summer. So we found these are tricky climates. I think my conclusion would probably be that cool external colors are very important to keep solar radiation reflected off the building envelope and reduce transmission heat gains. And then working with night ventilation, trying to create stack ventilation, have an opening on the lower floors of the building and another opening higher up to get air moving through. All, of course, like I said in the presentation, in coastal climates, many of which you have in Portugal, night ventilation is not always going to be useful when it's very hot in the night, but I think for a lot of the period of the year that can be useful. So cool external colors, which are cheap. You just have use a finish which is a light color, and then natural night ventilation is just a question of designing openings so that they can be used safely, no insects, no rain getting in, and so on in the nighttime. So I would say perhaps those two would be the most simple and cost effective. Yeah.
Okay, thank you. I have a little question, a smaller question. You show a fan in the roof. Do we have considered that in PHPP?
Good question. Yes, you can consider it in PHPP. In fact, there's a calculation. I didn't show it in my presentation, but there's a calculation which you can use from the ISO 7730 international standard. It's a fairly simple calculation you can use to calculate the effective temperature based on the wind speed from a ceiling fan. you can't use that to certify a passive house building. Unfortunately, it's not, well, it's not within the criteria of a certification in passive house. Doesn't mean you can't use it and take it into account. So, you know, you can adjust those temperatures in your PHPP to see how they might affect internal comfort. So, but like I say, you can't use that to justify certification of a passive house building.
Okay, thank you. Also for you, and after I pass for George, what's happened is that some people complain about the air and convective cooling system that are not so comfortable as in some cases you mentioned in your presentation that for passive house this is a less issue. Could you elaborate a little bit about that point, please?
Of course. Yes, I mean, we're talking, you know, the systems I presented are sort of systems 5 and 6, you know, where we're recirculating indoor air with a fan coil unit or a split unit. I mean, I think the point is in conventional buildings, which have in winter large heat losses and lots of air infiltration, you have to run these systems with a high flow rate. So there's lots of hot air being blown over you. Big difference in temperature between that and the surface temperature. So it's uncomfortable. Whereas in a passive house, you have all the temperatures at a much higher level in the winter because you've got good insulation, very limited thermal bridging, and no air leaks. In the summer, because you have a good envelope as well, and you have shading devices on the windows, and you're stopping as much heat getting in as possible, again, you can run these systems at a lower flow rate, which means it's not so uncomfortable. You don't have this cold air jet running, you know, blowing over you. You can run them at lower flow rates. They're therefore more silent. You don't have the noise of a fan. It's more comfortable acoustically. And you can run them even at slightly higher temperatures. So I think that means that these kind of systems in a passive house can be much more comfortable than in a conventional building. And they can be run quite efficiently because you can run them at low flow rates. So I think that's the kind of point I'm trying to make. And I think for all of the climates that we have on the Iberian Peninsula, you know, Spain and Portugal, Mediterranean areas, these are useful systems because they give you heating and cooling in the same system. And you just have one system which you can use in the winter and in the summer, and they have enough power if you need additional power, you know, during heat waves or during very cold moments.
Okay, thank you. I think also João Gavião have one question. Do you, João, can you put your question, please?
Yeah, it's just to have Oliver's opinion on this. The ventilation systems with energy recovery, not only heat recovery, but with energy recovery, they can bring any significant input to reduce the cooling loads. Do you have any feedback on that?
Absolutely. That's a great question, and I will add that to my presentation the next time I'm invited to a conference like this, because it's a good point. I mean, energy recovery ventilation, these are systems which, as well as recovering heat, they recover moisture. So when warm and humid air comes from the outside of the building and it goes through the heat recovery unit, the air that enters the building has less moisture. So yes, these are useful definitely useful for very humid climates, for coastal and very humid climates. You can see the effect in the calculations on the PHPP. So I would recommend using energy recovery or an enthalpy heat recovery units in very humid climates. Absolutely. They're also useful in very cold climates in the winter because then you don't need to preheat for frost protection. So that's something to bear in mind in very cool climates. But yes, enthalpy heat recovery is definitely useful in very humid climates. Yes.
Thank you very much, Oliver. Perhaps I would like to ask Juraj. You have spoken about that concrete foundations will have huge impact, and also João Pimpão highlights some of the alternatives options. After your experience today, what do you think that could be for future houses approach that have the same contributions that can be less intensive in carbon, because today is not only the operational but also the embodied carbon that is important. Could you highlight a little bit what you think after you do your nice house?
Yeah, sure. Yeah, it's always a difficult decision to kind of deal with foundations, and they are very specific for each site. You know, some sites are complicated and they require certain foundation approaches and design. So there's no sort of one solution to cover all bases. I mean, if we absolutely had to use concrete, we would probably look at reducing the cement content. So there are ways of substituting part of the cement with other lower impact materials, such as GGBS or fly ash or something like that. But we would also kind of explore alternatives which are sort of not based on concrete. So I mentioned in my slides whether we could look at suspended timber floors. So basically have like piled solution and then suspend the whole house, create like a bit of a crawl space underneath, sort of ventilated space, and have insulated timber floors suspended off the ground, which is something that is quite commonplace in parts of America, for instance. I mean, it comes with its own complications, but it just massively reduces the embodied carbon. If that's not possible for whatever reason, we could also look at alternatives like foam glass as an insulation, plus something like limecrete instead of concrete. I mean, limecrete has much lower embodied carbon compared to standard concrete. Or, you know, using something like clay floors as well, laid on foam glass. So there are all sorts of different alternatives which are sort of non-conventional. So you would also need to sort of talk to your structure engineers and building control, and sometimes, yeah, it takes a bit of persuasion to get these kind of non-standard approaches kind of approved. But I think we really, as designers, need to kind of look hard at these options and really try and lower the impact, because yeah, it's just, yeah, so urgent at this point in time.
Okay, thank you. Another point in your presentations that highlights in most of the slides is that you look for what perhaps we can call it bio-based materials, more or less.
Yeah.
And in which they are used traditionally in old times. After with what we call the change of technology, some of their technology are lost, another we are discovered, and things are important. With your experience, what you see that is the biggest barrier to have a larger adoption of these bio-based materials? We have also in Portugal, for example, different types of materials in which we use with earth and other things, and we have also some associations that promote that type of solutions, and in Algarve and in the north we have some houses building with this. And so my question is more or less, what you think that are the barriers to the adoption of these bio-based materials, if you think about that already?
I mean, I can't say for Portugal, because obviously I'm not familiar, but in UK, I think obviously the construction is very conservative, the industry, so most people are familiar with designing with concrete, with steel, etc. And use of materials like straw or paper as an insulation, or any other sort of natural materials is kind of on the outskirts. It's more of a niche kind of specialism. So I think education at kind of university level, you know, when architecture students go to school, it's kind of getting the message out there that, you know, you don't need to sort of design with steel and concrete. Yeah, there are other alternatives which are totally valid. but also kind of working with warranty providers, mortgage providers, insurance companies, and kind of get those people on board, because without them, we can't really win this or kind of get a sort of bigger slice of the market. I mean,
so
just
enlarge a little bit the actors, correct?
Absolutely. Like for information, in UK, natural insulation, it forms only 1 or 2% out of the whole market. So it's tiny proportion. So, you know, there's a huge scope to kind of rebalance that.
Yeah, thank you very much. I open also to other questions are available. We have more or less a couple minutes. If not, I put the questions for both. What is amazing, for example, when João Gavião and João Marcelino began to promote some of these houses in Portugal, it's very difficult to obtain equipment, materials, and other things. And now there is a full set of equipments, even that, of course, designers try and clients try to have innovations and things like that. So how do you see when you design and the options that you have, how do you see in your market the available of these solutions from at different levels, from Windows, from others that are certified passive house, and how you see that is the trend of increasing that opportunity, because it's an important area for you. We assure that you design also with passive house level. So, and my question is not only for the two persons, but I can also include in João Marcelino if you want to elaborate, or João Gavião. Okay, so I began by Oliver. How you think that the offer, the passive house certified materials and equipments have been changing the last 10 years, for example?
I think Spain, in Spain, at least what I've seen, there's been an explosion of certified components, particularly window frames, increasingly airtight materials, timber particulate boards. There's been a couple of heat pumps certified. I mean, I think the biggest growth has definitely been in window frames and windows. So I think that's really, really positive, because I think one of the great things, many great things about passive houses is it provides a stimulus to the market for innovation and new products. And that's really, and locally made or regionally made or nationally made products, which can create, strengthen local economies and circular economies. And so I think, at least in Spain, that's what we've seen. Of course, you can use many non-certified components to certify passive house, but obviously there are specific ones that are very useful that if they are certified. So I'm not sure how the situation is for you in Portugal, but I hope that it would provide the same stimulus to manufacturers in Portugal and different countries, because I think it's really interesting getting local, national manufacturers to adapt their products, improve them, and get them on the market.
Thank you very much, Oliver. George, please.
I mean, I think it's very similar in the UK to what Oliver has described. There's a huge appetite for passive house. We are certainly keeping very busy as kind of passive house architects here. I think at the moment most of the components are imported, unfortunately, but that is slowly changing. So yeah, I would hope that within the next few years there'll be more manufacturers, more specialists who will start making these components and make it more competitive. So that the overall sort of cost premium will go down, and eventually might even sort of get cheaper to actually build a passive house.
Okay, thank you very much. João Gavião and João Marcelino, do you want any telegraphic comments about Portugal supply?
I think the picture is pretty much the same that Oliver and Juraj share with us. Since we have the major players, they are global companies worldwide and in Europe, so automatically they made available at our market certified solutions. We have now, since a couple of years ago, the first certified components from national-based companies in Portugal. So it's a step-by-step process. I think that the manufacturers see Passivhaus and these high-level performance buildings as opportunity to present excellent products. But on the other hand, we can do, and that's the beauty of Passivhaus in so-called happy climates like ours, we can do Passivhaus with relatively simple components. We don't have to bring anything special to a Passivhaus that we have to use in a standard building. So this is something, obviously, including the air tightness and the ventilation systems that unfortunately in a standard building is still not very common. But I think that we are facing now, we have now a good foundation to build passive houses. When we started this process,
it's tough.
10 years ago, it was more difficult because it was a new language that everyone was learning. Now it's pretty much simple, and the future is bright.
Thank you very much. I'm going to close, but I will ask to our keynote speakers to give a last message, and I will thank you first and last by Oliver. So Oliver, keep cool and carry on. Last message, please.
Last message, well, there is hope. Keep working on your projects. Passivhaus is a great solution, I think, for the construction sector, and I also hope we can have an attending conference and see each other all in person one day in Portugal or elsewhere. So thank you very much.
Thank you very much. It was a pleasure. Juraj, from your house experience, it's not only a design, but also a user. So all the way project, last message or key message, and thank you very much also for your presentation.
Yeah, no problem at all. It was a pleasure. Yeah, just keep doing what you're doing, you know, great projects, and consider using natural materials where you can, because we really need to sort of consider embodied carbon, upfront carbon, as well as the operational. So I think that's where the kind of focus, because we can do energy, you know, once you kind of sussed it, it's quite easy. I think the next big thing is to kind of look at materials. So yeah, quite excited.
Thank you very much. I would like also to thank to Passivhaus Association and Home Green by the organization of this conference in which make experience, and all the participants here that thank you is for you that the conference it's over there. And I will finish and thank you very much, and with your clap your hands by our keynote speakers, please. Thank you very much. Is closing the section 3, and I hope you go on in the conference Passivhaus, the 9th conference Passivhaus. Thank you, Oliver. Thank you, Juraj.
Thank you. We will close the session in Portuguese now. Thank you, Oliver and Juraj, once again. Vamos então só fechar aqui a sessão. Queria agradecer uma vez mais já a excelente moderação do Manuel Duarte Pinheiro. Muito obrigado, Manuel. Vocês podem já aceder e partilhar estas excelentes apresentações. Já estão disponíveis para ver e rever, tanto em PDF como também em vídeo. Já podem então aceder a essa informação. Só lançar novamente aqui o apelo, portanto, juntem-se a nós, venham construir o futuro que queremos connosco, venham fazer parte desta rede Passivhaus cada vez em maior crescimento. E um último agradecimento então aos nossos parceiros de comunicação, aos nossos parceiros institucionais e aos nossos parceiros estratégicos, e um obrigado e um agradecimento final a todos os participantes pelo interesse demonstrado. Continuamos então na quinta-feira com o último dia da conferência e esperamos encontrar-vos novamente na quinta-feira. Muito obrigado.